So I had actually already started recording some of this for period 3, but then the projector messed up. Let me know if it messes up again. What happened is it froze last time. I don't know why. It wasn't the iPad that froze, like the projector itself literally froze. It was weird. So just keep an eye on the timer. If the timer stops, something messed up. So this time we're talking about conservative forces versus non-conservative forces. Okay. Give you guys a second to write that down. And it all comes down to the definition of work. We'll look at that in a second. Okay, so when we look at work, we're looking at this force done, .dr. Again, it's really important to understand what the definition of work is in a very visual way. Let's say you have an object that's trying to get from point A to point B. Okay, and it's being pushed there by it could be being pushed there by different forces. Different forces can be acting on this object that's trying to get from A to B. And let's just say that this object gets to A to B by this path. Okay. Some completely arbitrary path, it doesn't matter. The force that we're interested in, a particular force that's acting on it, we'll say is force F. And at various locations, it is pushing always in the same direction. And I'm trying to diagram this as best as I can. It's always pointing in the same direction. Something like that. Right? Kind of like gravity. Okay, it's always pointing in the same direction. Maybe it's the same everywhere. Maybe it gets bigger as you go from left to right. Doesn't matter. The point is that if it is a conservative force, we said that conservative forces tend to be forces that are only a function of position, or in this case, it's constant everywhere. Okay, that's really important. As we'll see, as this object actually travels along this way, the path that it takes can change. Right? These are all little vectors. Vector F, vector F, vector F, vector F. And this is a little dr. Okay, so at one moment it's going a little bit more up and a little to the side, and then here they're in line with each other. You see that the dot product says you only take the component of the force that is parallel between the two vectors. Okay, how much are they in line with each other? Here, they're maybe 45 degrees in line with each other. Here, they're entirely in line with each other. Maybe right here, they're hardly in line with each other at all. Okay, so sometimes the force is contributing to its motion, and other times it is not. Completely. Maybe not completely, right? One thing that you'll find about a conservative force is that it the work done by it only depends on where it started and where it ends. It doesn't matter if it went like this. It wouldn't matter if it went maybe like this. It doesn't matter. If you look at how we would add it all up, that the force is always pushing to the right. And really, if we want to specify that it's always pushing kind of in this line from A to B, when it goes up, it will effectively have the same result as if it just went in a straight line. The work done by F will not really differ from whether it went in a curved path or went straight from here to here, because it's only the part that's pointing in this direction that's adding work to it anyway, right? Maybe another way to think about it is if F is pointing from A to B, and you're only taking the components of R that are in the direction pointing along F, right? Then at any moment, you're only taking the component that's along the straight line path anyway. Does that make sense? Think of it like these positional changes at every spot, they have like a coordinate value like X and Y, right? At the end of the day, F only works with the component like in the X direction. And it doesn't really have any component in the Y direction. So it doesn't matter if it has changes in the Y. It only matters that it has changes in the X. And those X changes are effectively the same as if it just went in a straight line anyway. At least as far as the work done by F. Okay. In other words, I have this gravity or something pushing on it to the right, and how much energy is transferring to object due to this force doesn't really matter what path it takes. If that's the case, then we can write a function called potential energy, and we get that relationship. Okay, so this only exists for conservative forces. Conversely, if it does exist, that means it is a conservative force. Yep. Oh, yeah. If it is a conservative force, there's a potential energy function that exists. Or if a potential energy function exists, that makes it a conservative force. That means that as it goes to the right, it will gain energy irrelevant of its path taken, only that if it goes from A to B, it will have gained a certain amount of kinetic energy. Or if it gets pushed against the force, it will have gained a certain amount of potential energy. Doesn't matter whether it goes up or down, as long as it goes from B to A or A to B, there will be a fixed potential energy change. Okay. That is the essence or the important part of a conservative force. Okay, so I can say something like this. Starting at A, it might have 30 joules of potential energy. And I'm trying to avoid saying specifically gravitational potential energy. Some of you guys ask, why is it sideways? I did it specifically sideways because it doesn't have to be just gravity. There are other forces out there that behave in a potential energy-like fashion. Frankly, if you look at gravity, even for gravity, gravity is only quote-unquote up and down because that's just our reference frame, right? But if you start leaving the planet Earth, there's still gravity, but what's considered up and down? You know, it could be in any direction, right? So it's not necessarily necessary to tie yourself to an up and down notion of gravitational potential energy. So you can have like 30 joules of potential energy here, and this would be 10 joules of potential energy over here, and this is just an example. But the idea is, if this object were to take this path, the energy that the potential energy that it loses from here to here would be 20 joules. Sorry, from here to here it would be 20 joules, whether it went up and down, or if it went straight across, or it went down here and here, right? Maybe another way to think about it is, if I take an object and I just drop it, it changes a certain height, right? So it loses a certain amount of gravitational potential energy. How much potential energy does it lose if I shoot it and it falls sideways? It's the same, because it's still falling the same amount. So gain the same amount of kinetic energy from gravity and so on and so forth. So the path that it takes for a conservative force doesn't matter. Okay, it doesn't matter. Okay, so some examples of conservative forces. You know, we already looked at potential energy from gravity would be like mgy, and that the potential energy from a spring is like a 1/2 kx squared. But the list goes on. There are other ones. You can keep going. There are more. And what we're trying to do is start generalizing this to any kind of force that acts in a conservative way. The hallmark of a conservative force is that when it goes from A to B, there is a fixed amount of potential energy loss. And when you go from B to A, there's a fixed amount of potential energy gain, no matter what path you take. That's what makes it a conservative force. Any questions about that? It can be kind of tricky to, it's a very conceptual thing, very, very abstract, like super abstract. So I wanted you to visualize it kind of like this. If you have an object at a certain height, right? Let's say I'm like walking around, right? When I go this way or this way, my gravitational potential energy relative to the floor doesn't really change. I'm not getting higher, I'm not getting lower. So you can say that along a flat surface, as far as gravitational potential energy is concerned, it has all the same potential energy, right? Or if you get on top of the desks, right, you're a certain height away from the floor. But this desk is no different from any other desk. If they're all the same height, that is another kind of a level of potential energy. So we call that an equal potential surface. An equal potential surface is a surface where everywhere along that surface, they all have the same potential energy. Okay, so for example, in this case, I might draw my equal potential surface like this. That is equipotential surface. And I say it's a surface because three-dimensionally, it's like a boundary. It's like a boundary. So everywhere along here, any object on this line would have 30 joules of potential energy relative to this force. Right? So that if it goes from here to here, or from here to up here, or here to anywhere along this line, it's still losing 20 joules of energy. They have the same potential energy loss from here to here. Okay. Let me try and give you something very concrete to try and tie this together. Have any of you guys played Wii Golf? Okay, in Wii Golf, if you go to the options, you can turn on a special mode that does something to the, it gives you the contour map. What does it do? Do you remember? How does it display it though? Different colors. It does different colors. With contour maps, right? You see contour maps of mountains where they have a bunch of kind of like ridges or something like this, right? What do those lines usually represent on a contour map? Yeah, Mike. Elevation. So this might be 500 feet, this might be 600 feet, 700 feet, 800 feet. Contour maps are equal potential lines or surfaces for gravitational potential energy. They're all the same energy anywhere along this surface, right? Or actually along that line. Sorry, I shouldn't say on that surface. It's along that line, right? Because the idea is as you go inward, you're going to a higher elevation. So you could imagine there's an infinite number of these contour lines in between each contour line, but this might be like 500 feet, 600 feet, right? So everywhere along the line is supposed to be 500 feet or a certain amount of potential energy. It's kind of the same thing in Wii Golf, except that instead of lines, they do color. I think the deeper you are, the darker the green, and then the higher you are, the lighter the green or something like that. But the idea here is for a certain color, any spot with the exact same color should be at the exact same elevation, same height, or therefore same potential energy. So what does this tell you about the direction objects want to go? An important thing to note about potential energy is potential energy. Oops, potential energy is related to the force through this integral. If we do it in reverse, what we find is that if the integral of the force gives you the potential energy change, then the instantaneous rate of change of the potential energy with respect to position, okay, with respect to position, not time. How does your potential energy change over a really small gap is related to your force. Okay, so look at these two graphs. Okay, your force over a certain position, if you're changing position with that force, that area under this graph is how you're losing potential energy. Okay, as your force pushes on the object in that direction, you lose potential energy, right? Gravity pushes an object down, it loses potential energy as it falls down. Then conversely, if you look at your potential energy versus position graph, as an object is moving, if it is gaining potential energy, then the slope of that line is the negative of your force. The negative is important. If you are gaining potential energy, your force must be pushing in the other direction. That is the nature of potential energy. To gain potential energy means something must be pushing in the opposite direction so that it kind of gives you that restorative stored component. Okay, just for as an example, so you can make sense of all the calculus here, let's use gravitational potential energy as an example. We already said that the gravitational potential energy is equal to mgy. So what is the derivative of this with respect to y? A change in y, this is a linear function, the polynomial of exponent of degree 1, that just makes it mg, right? Which is equal to the negative of the force. The force of gravity is in the negative direction of changes in y. Okay. So there's a couple of important things that come from this. Unfortunately, when we're dealing with energy, energy is a scalar value. Force and positional change are vector values. And I kind of use them interchangeably in not a very precise way. So when I do this, this is implying automatically that this is the component of the force in the direction of positional changes. And this is potential energy change in the direction of positional changes. So what this tells you is that you only have potential energy change in the direction of the force, which means that you should have no potential energy change in directions perpendicular to your force. In other words, this implies that F is always perpendicular. Oh goodness. Can you guys read that? F is always perpendicular to equal potential lines or surfaces. F is always perpendicular to equal potential lines and surfaces. This is going to be a very useful concept when we get to gravity, which is pretty soon. We have rotation next, and then we get to gravity, and then we get to electric fields. In both of those cases, it's very useful to look at equal potential lines and equal potential surfaces. That's where the whole concept of voltage comes from. It's actually really important. So trying to start introducing the concept now. Okay. So let's look at the meaning behind this. If F is always perpendicular to equal potential lines and surfaces, that means that F is perpendicular to this dotted line here. And so at every location, you can kind of draw an equal potential line. I don't know if you guys can kind of see that. Let me do a better dotted line. Right? At every location, you should be able to draw an equal potential line that's perpendicular to the direction of the force. What that lets you do is that means that your object is always falling perpendicular to your equal potential lines. That should kind of make sense. If you take a ball and you dropped it right here, how do you decide which direction it wants to go? Yeah, we say it wants to fall downward, but how do you use the visual cues of the equal potential lines to determine where it wants to go? It should always go perpendicular to the surface, right? Or if you put it right here, where does it want to go? It wants to go perpendicular to the surface. Or if it's closer to here, it wants to go perpendicular to the surface, right? Every time it should be trying to be perpendicular to that. Does that make sense? So think back to Wii Golf or just golfing in general, right? How do you decide where the ball is going to go? It doesn't go necessarily. The tricky part about this is when we sketch these out, this is the direction that the force is pushing on the ball all the time. Whether it actually follows this line, it's kind of hard to tell because, as we said before, a force is an acceleration, not necessarily a velocity. So if it's very steep, it may have like fallen off the cliff before it even has a chance to fall in that direction. Does that make sense? The forces are along these lines, and so we can kind of try and approximate that it wants to go along that path. That's how the energy changes want to go. But if it's falling really fast, it may roll further than the forces can push on it in time to change its direction. I don't know if that really, does that make sense? Trying to think of, well, all right, well, we will see more examples of that later on, but let's see. Okay, I want to draw another example then of contour maps, okay, of these equal potential surfaces. Let's say I have a surface that looks like this, and then it looks like this, and it looks like that. Okay, another example. For each surface or line, we can give it a certain amount of energy. Let's say this is 30 joules, 20 joules, 10 joules. Okay. What this should tell you is that anywhere along this outer line that has 10 joules of potential energy. Again, not necessarily gravitational, but whatever the force is that's affecting this object. It's like 10 joules, 20 joules, 30 joules. If I go from here and I try and follow my perpendicular path, right? By the time it gets to here, it should have lost 20 joules of potential energy. Same thing if it goes like this way. Right? And same thing if it goes this way. So here's the thing. If it loses 20 joules from here to here, or it also loses 20 joules from here to here, or it also loses 20 joules from here to here, they're losing the same amount of energy, which means they gain the same amount of kinetic energy. So what is the difference between those three paths? What makes them behave differently? Yeah.
They're different lengths.
Different lengths. So what does the length physically represent, do you think? Not just distance, but in the behavior of the object that's moving. What's that? Displacement. They have different displacements. This is a shorter displacement. It is transforming that energy not faster. It's transforming that energy in a shorter distance. So what does that tell you Oops. What does that tell you about what's acting on it? Mike. Not necessarily gravity, but whatever's pushing on it. Maybe this is kind of a stretch. I'm kind of asking pointed questions. If it changes the same amount of potential energy in a shorter distance, doesn't that mean it has a stronger force acting on it, right? If dr, if the change in the distance is less for the same amount of potential energy change, it must be accelerating more here than it is over here, right? You must have a stronger force here than you have a force here. Does that make sense? Your equal potential lines can really give you a visual representation of what your forces are acting like, or have you guys done vector fields in Calc AB? The other class told me you guys did like the slope. What do you call them? Slope fields or something like that, where you do a graph and then you say like the slope is like this, and then it's like this, and it's like this, kind of like that. Right? You do that everywhere, right? This is like these would be like a plot of all your forces everywhere. Your equal potential lines then would be perpendicular to all of those. That would be your equal potential lines. They are kind of counterparts, two sides to the same coin. The lines that connect perpendicularly to all those slope fields, those are your equal potential lines. And then your slope fields are all pointing in the direction of where it wants to go. Okay? Okay. Any questions about that? So this all goes back, okay, so this all goes back to conservative forces. What we want to use conservative forces for comes down to this. Very fundamentally, the net work done on an object leads to its kinetic energy change. What we can do is we can take the work done by all sorts of forces acting on an object and split it into two kinds of forces. Two kinds of work. Work done by a conservative force and work done by a non-conservative force. A non-conservative force is a force that cannot be written as a function of position. It is a force that changes depending on what kind of path you take. So think of friction. If I push a cart from here to where Dhruv is, and I take a really curvy path, right? The amount of friction that I experience and the work done by my friction will depend on how curvy my path is. But if I take an object and I drop it, the amount of kinetic energy change from gravity is the same as whether I drop it or whether I throw it. It's the same kinetic energy change. The same gravitational potential energy loss. Okay? So there are conservative forces and there are non-conservative forces. Conservative forces we can represent with some sort of potential energy function, right? We can add up all our different potential energies, whatever it is, but there's some change in potential energy, whether it's gravitational or maybe it's elastic, whatever it is. You can represent the work done as some change in potential energy. There's a function there. It's kind of nice. Your non-conservative work, we can split up into two kinds of work even further. You have dissipative forces, and you have every other kind of force. So we split it up into dissipative work and then external work. Okay. Turns out that in the universe there really aren't that many different kinds of forces. Okay. For example, things that fall under external forces would be like tension, normal force. They're not dissipative forces. They don't transform mechanical energy into thermal energy. Dissipative forces, so like tension, person pushing, whatever, right? You have contact forces. Contact forces. Dissipative work is usually from like friction, drag. Those are kind of the main ones. These will always oppose the direction you move. Okay? Friction is always in the opposite direction of movement. Drag is always in the opposite direction of movement. So we call those dissipative forces. That's why we always say it's a negative work. While these can be pushed in the direction of movement. You can push on it, you can pull it along with you, you can pull it with a string. Even normal force, as you go around the loop, it pushes you up. Right? Then all of those will equal to delta K. So what we can say is that the external work